Hi, everybody. So in this lecture, we're going to practice balancing redox reactions in acidic solution using the half reaction method. As I mentioned before, you guys are responsible for balancing redox reaction in acid only, not in base. So here in this handout, I've outlined a strategy to figure out how to balance any redox reaction in acidic solution. You should use this half reaction method to balance any redox reaction, no matter how simple, because it is a foolproof method. And you basically want to practice using this method on many, many different practice problems until you don't even need the sheet anymore. You can just do it automatically. It's important to follow these steps in order to get a perfect result. So looking at the strategy, the first thing you want to do is figure out the oxidation states of all of the elements in the reaction and determine which element is being oxidized and which element is being reduced. So I'm going to give you guys an example reaction, that I want to use to test this half reaction method. So we're going to take solid copper and silver ion in aqueous solution, and we are going to produce aqueous copper 2+ ions and solid silver. So let's do the first step for this reaction. We want to figure out the oxidation states of all of the elements in this reaction. So in doing that, I want to remember that elements in their pure states have oxidation states of 0. So the oxidation states of both copper and silver solid are 0. Now, the oxidation states of silver plus and copper 2+ are given by their charge. So the silver ions here have a +1 oxidation state, and the copper ions have a 2+ oxidation state. Now we want to determine which element is being oxidized and which element is being reduced. And in order to do that, I'm going to teach you guys some vocabulary here. And I know you guys learned about this last semester probably, but just to refresh your memory, this mnemonic device is very useful. Leo the lion goes grr. And of course, that stands for lose electrons, oxidation, that's Leo. And grr stands for gain electrons, reduction. That will just help you remember what oxidation and reduction actually means. When we talk about redox, we're combining both of them, but it's important to remember that reduction means that you're gaining electrons, so you're becoming more negative, hence the word reduction. You're becoming more negative in charge. And the oxidation means you are losing electrons, so you are becoming more positive in charge. So now looking at this reaction, we can figure out which element is being oxidized and which element is being reduced. So copper is going from 0 to 2+. It is losing, so each of these is losing 2 electrons, right? To go from 0 to 2+. So copper is being oxidized. I hope that's clear. Copper is being oxidized from Cu0 to Cu2+. Okay, so that means, of course, in any redox reaction, one species is going to get oxidized, and that means that some other species has to get reduced. You cannot have one without the other, because you have to have electrons transferring from one thing to another. So silver must be being reduced, and indeed you can see that it is. It's going from +1 to 0. So that's a 1 electron reduction, right? It's becoming less positive, it's becoming more negative. It's not becoming negative, but it's actually just going from +1 to 0. So that's a 1 electron reduction. So we can say that silver is the element that is being reduced from Ag plus to Ag0. Okay, just a little bit more vocabulary. So the silver is being reduced, and that means that we would call this Ag plus the oxidizing agent. Okay, so Ag plus is the oxidizing agent. This is a little bit confusing for students because basically you're just like shifting the point of view, but this species that gets reduced functions as the oxidizing agent. So basically, this species is responsible for oxidizing the copper, so we would call Ag plus the oxidizing agent. Conversely, copper 0 is the reducing agent because it is getting oxidized, and in the process, it is reducing the silver. So students struggle with that a little bit, but that's kind of important vocabulary to know, that we would refer to solid copper as the reducing agent because it is reducing the silver. Okay, so just to sum that up, the species that becomes oxidized is the reducing agent. The species that becomes reduced is the oxidizing agent. That's going to be true for any reaction. Okay, so we've done steps 1 and 2. We figured out the oxidation states. We determined which element is being oxidized and which element is being reduced. Now, step 3, you want to separate the reaction into 2 half reactions, 1 oxidation and 1 reduction. So this is an easy one to do because I just need to take the silver or the copper and kind of separate it from the silver. So I can just take that whole reaction and split it into 2 half reactions. So on the top here, I have the oxidation half reaction, and on the bottom I have the reduction half reaction. Okay, half reactions are purely a conceptual construct that you use to help you balance reactions. Half reactions cannot happen by themselves. You can't have reduction without oxidation and vice versa. The electrons have to go somewhere. But these are just a tool that we use to balance redox reactions. Okay, so we have the oxidation half reaction and the reduction half reaction. Now we go to step 4. For each half reaction, we want to balance all of the elements except H and O. This is very important. You have to do these steps in order, and it will simplify your life enormously. So in this case, we have 1 copper on each side, so they're already balanced elementally. Same with silver. We have 1 silver on each side. So we don't need to do anything for that one because they're already balanced. In the second step, you want to balance any oxygens by adding H2O. And in this very simple example that I'm starting you guys with, I don't give you any oxygens here, so we don't need to worry about this one either. Same with the H's. We don't have any H's in this particular reaction, so we don't need to worry about balancing the H's. However, we do need to worry about balancing the charge. Because if you look at the half reactions, they are imbalanced in charge. The charge of the reactants is 0 here, and the charge of the products is 2+. The charge of the reactants is +1 here, and the charge of the products is 0. The only tool that you are allowed to use to balance charge in this last step is electrons. So you have a negative thing that you need to balance the charge with. So let's deploy that for balancing the chemical reactions up here, the half reactions. If I need to use electrons to balance the charge, on the top reaction, I'm going to have to put them on the right side because then the 2+ will add to the 2 minuses and make 0. So now my half reaction is balanced in charge on the left and the right. You needn't necessarily have it 0 on both sides. They just have to be equal on both sides. Then, for the bottom reaction, I have to add an electron to the left side. And now when I add that 1 minus charge to the plus charge here, I have no charge on the left, which equals the 0 charge on the right. This makes sense, right? Because for the oxidation half reaction, I'm losing electrons, so they should pop out on the product side. In the reduction half reaction, I'm gaining electrons, so they should be added on the reactant side. So I balanced the charge of each half reaction by adding electrons. Now, the fifth step is to add the half reactions together. However, it's very important to note that if necessary, you have to multiply by some integer to equalize the number of electrons transferred. And in this case, if I'm adding these reactions together, I need to be able to cancel out the electrons that are transferred. So I'm going to take the bottom reaction and multiply it through by 2 so that I can equalize the numbers of electrons transferred, and I can kind of cancel them out. So let me show you that. I'm going to show you in a different color. I'm going to take this whole reaction and multiply it by 2. That means that when I add them together, I'm going to copy them down again. I have the solid copper going to Cu2 plus 2 electrons. And I'm on the bottom going to have 2 electrons plus 2 silver ions. I have to multiply the whole reaction through by 2, the stoichiometric factor. So now I have 2 reactions and I can add them together. It's crucial to equalize the number of electrons transferred, so when I add the electrons together, I can cancel out those electrons. And now I'm going to add those reactions together, so I get solid copper plus 2 silver ions, giving me 1 copper 2 plus ion plus 2 silvers, solid silvers. Now the final step is to check your work to make sure that it's balanced in both elements and charge. So I have 1 copper on the left, 1 copper on the right, 2 silvers on the left, 2 silvers on the right. My overall charge on the left is 2 plus, and my overall charge on the right is 2 plus. I am balanced. Yay! Now you may say, that is so simple, I could have balanced that by inspection. Sure you could have, because I'm starting you guys off with a very simple example. However, when it becomes more complicated, it will be very difficult to balance these things by inspection. So I'm using this very simple example to teach you guys how to use this strategy. In the next lecture, I'm going to do a much more difficult example that will illustrate the importance of the half reaction method in balancing chemical reactions that are more complicated. Okay, so I hope all of that made sense. In the next lecture, we will try another more complicated redox reaction.